Hello everyone, and welcome to our next session. Today's lecture is going to be on following up on the story of our mountains, known as the Himalayan Tibetan Orogen. Now, this is a concept that we're going to be returning to many times throughout the course because it will really sets the stage for the landscapes that we see. So, this is my first time putting together this presentation and our first time talking about it, and I know there will be a lot of questions. But just like we talked about last time, questions are what will drive our understanding forward. So let's give it a go. Our wonders about tectonics, right? These are what's driving our presentation today. We wondered why earthquakes don't happen everywhere at the same magnitude. And last session, we learned that it's different tectonic forces and fault settings which produces earthquakes of different magnitudes. Our next questions are, we wonder why there are more faults in the eastern region of Bhutan, and we wonder why different regions of our country are categorized into different tectonic and earthquake zones. These two questions are going to drive our presentation for this session. And to answer those questions, we really need to, again, look into the story of these mountains. And when we talk about the story of these mountains, we refer to it as the Alpine Himalayan Orogeny. The term orogeny is simply a geologic term that means a mountain building event. And we are going to be focused on the Himalayan Tibetan Orogen, which is just one small part of a larger global system. But by focusing in here, we'll be able to gain an understanding of these broader tectonic forces. Now, when we think about the Himalayan Tibetan Orogeny, maybe you've seen a map like this before. And oftentimes, these maps can really appear confusing. However, when we take away some of the extra detail, researchers for the past 50 years have really come to the understanding that on a broad scale, the Himalayan are relatively simple as an orogenic belt. So my question for you is, what do you notice about the colors of this map? What can you see? After some quick observation, I bet you could notice that there are some broad strokes of similar colors all across our mountains. We have a top section right here, a middle section in pink, and then a green section, which is kind of mashed up in between. And the distribution of these colors is going to be the driver of our story for today. So rather than looking at all of the mountains at once, we can focus in on just a subsection around Bhutan, around what we're familiar with, in order to gain a broader understanding. And so when we look at a geologic map of Bhutan, and again, take away all of that detail and just look at the colors, again, we can see that some patterns can start to emerge. We have these green-colored rocks up at the top, a whole mash of different colors in the middle, but mainly pinks, and then these blues and other greens down here. And then all those colors really seem to terminate towards the bottom. So unraveling the story of these colors is going to be our mission for today's session. And to do so, I found one of the best ways to talk about geologic history is to really think of it for what it is, a story. So, in these next few slides, I'm going to share with you the geologic chapters of the Himalayan landscape. And once we complete these chapters, I hope we'll be a few steps closer to answering some of your questions. So let's begin. Chapter 1. When we think about the origins of the Himalaya, before the huge peaks of Gankarpunsum and Jommohar even rose above the earth, we have to actually go away from Bhutan. We have to think back over 2.5 billion to 152 million years ago. At this time, our landscape of Bhutan was not even in existence. But the rocks that would make up our mountains formed initially on the Indian subcontinent. Through much of its continental history, India has been what's known as a stable platform of continental crust with a border on the ocean, allowing sediments to be deposited on its northern flanks. And so, again, throughout history, we can see how the Indian continent was in this position, assembling into a few different supercontinents, first known as Gondwana, which it joined upwards of 500 million years ago, and then into Pangaea over 335 million years ago. Around 200 million years ago, Pangaea started to break up, and above India, the Indian continent, was a broad sea known as the Tethys Sea. And it's within these origins, in the Tethys Sea and in the Indian subcontinent, where the rocks which would make up the Himalaya were first deposited. So remember that. We got these sedimentary origins. Very, very old. But moving forward, the next chapter breaks into something known as continental migration. And this happened between 152 to 55 million years ago. Tectonic forces like we just learned about at these constructive boundaries was forcing apart the Indian continent from Gondwana. And we can see in this animation how India started to migrate northward. Over the years, as it migrated northward, the Indian continent began to rotate counterclockwise as it moved towards the Eurasian plate. An important thing to note about this progression is that it proceeded in a manner where India wasn't just simply drifting across the ocean, but this ocean was actively subducting. This animation really shows a good cross-section. But we can see, as this progression happens, as the Indian continental plate goes forward, the Tethys ocean plate was actually subducting beneath the Eurasian plate. And what's special about this is that as this subduction occurred, a lot of the sediment that was on the bottom of the ocean was scraped off at that subduction zone. This complex is known as a Creationary Wedge. This ocean floor sediments that are then actually thrust onto the continent. So not only do we have our Indian continental plate with those early sediments coming towards Asia, but we have scraped up ocean floor as well, setting the stage for this continental migration. All right, so let's move forward. Well, chapter 3, this is when collision actually commences. There's paleomagnetic data, there's data from rocks and there's sediments that shows us that the Indian continent began to slow in its migration around 55 to 40 million years ago. And this slowing down of continental progression is interpreted as our beginning of our collision. So we saw this animation in our last video, but we're going to be relying on it for the remainder of today's session. And as our continents come together again, we have that first buckling and thickening of the crust. But one important thing to note is that, again, these lighter colored rocks are part of these ocean sediments. So notice that accretionary wedge, that ocean sediment right here in between the continental collision. And this ocean sediment, you can see it moving across, is actually what forms some of the northernmost rocks up here. So this ocean sediment is part of this third chapter of collision. And if we look towards our geologic map, we can see that ocean sediment in the highest portions of the Himalaya around Tibet and up here. And so this type of rock is known as the Tibetan Sedimentary Sequence, TSS. And so these are ocean sediments that have been metamorphosed and upthrown onto the continent right here during these first parts of collision. So our collision commences, our convergence has begun, let's see where it takes us. Chapter 4, Faulting in the High Himalaya. Here's where it starts to get good. Between 24 and 18 million years ago, this continued compression and migration of our continents forced some pretty incredible changes in those original sedimentary rocks. The first thing that you'll notice from that animation is the development of one new line, and new division. And so this division up here demarcates this break between the Tibetan sediments and the rocks that are below it. And those rocks formed in this band right here. So let's take a look on our map. That red line up at the top is what's known as the Southern Tibetan Detachment System. In this instance, we had those seafloor sediments begin to push out and push backwards just as the underlying rocks beneath began extruding forward. And those rocks in the pink section are known as the Greater Himalayan Sequence. These are high-grade metamorphic rocks, things that have undergone immense amounts of heat and pressure as they were pushed up and out of the Earth's crust. So we have our first major faults becoming active in the Himalaya. Brings us to our next chapter, which builds what's known as the main central thrust. If we watch our video again from 16 to 8 million years ago, we can see that continued pressure has really forced up our rocks along those greater Himalayan sequence. Has really forced them up, and it built this new zone beneath it. So if we take a look at the map, that will lead us to this new section right here. Well, yeah, we have the development of a new fault system and a system of rocks beneath it. And so that fault is known as the main central thrust, active from those 16 to 8 million years ago. And as that became active, those higher, greater Himalayan sequence rocks began to metamorphose these lesser Himalayan sequence rocks, which were underneath. So again, these were older sediments that were initially deposited on the Indian shelf, but have now been subjected to different amounts of metamorphism along this main central thrust. So our mountains continue to grow, these faults continue to work, rocks continue to be metamorphosed, and as these mountains are building, they're also eroding too. We're going to be looking at this next week, but this erosion is taking place and depositing all sorts of sedimentary rocks on the base of these mountains. And these sediments are really going to be crucial at looking at the next chapters going forward. Chapter 6, Breaking of the Boundary. Now, from 9 to 3 million years ago, our compression continues. And as we watch these continents continue to collide, we can see again these new fault systems that are developed. And this boundary right here is known as the main boundary thrust. And it runs all towards the base of Himalaya. This main boundary thrust separates the lower Himalayan sequence from those foreland basin sequence down below it. And in some cases, even in western Bhutan, that main boundary thrust demarks the front portion of the Himalaya as they start to rise up out of the Indian plains. But this happened up to 3 million years ago, was when the main movement's going on, and the main boundary thrust remains active to this day as a fault system. This brings us to Chapter 7, the modern mountain front. We have our progression, which continues to this day. Continents are still colliding, going at a rate of almost 20 millimeters a year, which means that this main boundary thrust can't take up everything. And as you can see, we have the development of faults happening underneath. So this will build up what's known as the main frontal thrust, the newest fault within the Himalayan system. And the main frontal thrust is continuously active and altering these known as the Sewalik formland deposits, those rocks that were shed off of the Himalaya. Wow. And so this series of faults and series of rocks really makes up the division of our Himalayan systems. And it's the key to unlocking our earthquake distributions.